Okay guys, now in this video we're going to get into the programming of the actual we're actually going to use the I2C to program this chip right that you see right here. This is the exact chip that is right there. It's tiny little chip. It's obviously it's an 8-pin chip. Um, and it's an EEPROM, and there's a special way it likes to do things. So I'm gonna try to explain it because that obviously affects how I write my code, and that's how you're gonna find most I2C devices operate the same sort of principle, where you send it the address of the device, and then you send it an address internal to the device where you want to write data. And usually the data that you write is a command, and that command maybe you write on this internal address 4, you write the command 65, and that tells the chip to send you temperature data or whatever, so that's usually how these I2C chips work. So you send your address, you send another address, but it's not a slave address, it's an internal address of where you're going to write to. Now the way this one works is the same thing. So you're going to send it the address. The address for this chip is governed by these 3 pins. So it's by default the address is 1010, and then these 3 pins right here. So if they're all grounded, it's going to be 1010, then 000. So that's 7 bits. And then the like any other I2C chip, the last bit, or the least significant bit 0, is for reading or writing commands. So when it's a 0, you are writing to the actual chip. When it's a 1, you're telling the chip that you want to read from it, and it sends you data. Okay, so the way this one works is it's just memory. There's 256 bytes inside the chip, and it has all these basically locations, and in each location you can write a byte. So if I want to write, let's say, the word hello here, I would first I would send it the address that I want to write to, and then I send it the data. So I would first send obviously the start condition, then I would send the address of the chip, then I would send the first address that I want to write to. So I would send it 00. Okay, so that's already 2 bytes that I've sent, the address and this other internal address, the slave address, and then this internal address. And then the 3rd byte, I would start sending it the data. So I'd write like H, and then when you send it data, it by itself has like this little, that I've represented here, an internal pointer. Every time you write data to an address, it increments that pointer to the next address. So once I send it the H that I'm going to write here, it's going to move, and then when I send it the E, it's going to put it here. So it'll be HE, and then it'll increment its internal pointer and go to the next byte, and now just a LLO, whatever. So whatever data I'm sending it, I just got to send it the start address, and then just keep inputting my data, and it'll take care of incrementing to the next available address. It can only, however, do 8 bytes at a time. So if you're gonna write a really long string, or more than 8 bytes, you're gonna have to send it separate commands, like send another start condition, and send it a new address to start at the next page, which would be 08, and then start writing from there. So this chip can only do 8 bytes at a time. So that's when you're writing to it. When you're reading from it, you can just send a read command. A read command is nothing more than a start condition followed by the address, but on the 0th bit of the address, which none of these are the 0th bit. The 0th bit of the address has to be a 1. And you'll see in the code what I mean. I should have done like a little drawing for that. but basically you have an address, right? So pretend, ignore these numbers up here. So these is 1 2 3 4 5 6 7 8. So pretend this represents the address of my the EEPROM. So the default address of this is 1010, and then these 3 bits are represented by whatever state these 3 pins are at, right? So if I leave them all 0, they're all 0. Actually, it's by default. That's how that circuit was made. They're all zeros. They're all grounded. So then it's all zeros right here. So it's 1 0 1 0 0 0 0. And then if this is a 1, that tells the chip that I want to read from it. If this is a 0, that tells the chip I'm writing to it. So you should never send it the address with a 1 here and then try to do a write command, because that wouldn't make sense. You know what I mean? Because that the 1 implies a read command. So once you send it that read command, you just start waiting for your RxNE stuff. Flags and all that stuff. You start waiting for your data. Okay, so to read data from the chip, you can just send it a read command, which is the address with a 1, and wherever the pointer is at, that's where it's going to start reading from, right? So what if you want to start reading from here? How do you get the pointer over there? Well, remember that I told you when you do a write command, it increments the pointer. So if I wanted to read from address 5, what I would do is I would first write to address 4, and I would write basically nothing. I would just send it the address 4, and instead of sending data, I would generate a stop condition. And since I didn't technically write any data to it, because I may or may not want to overwrite what's here, it still incremented the pointer. So now the pointer is here. So you send it a write command for the address 4. You don't write anything. You generate a new start condition, and then you send it a read command, and then it'll read from this address. So it's a little, I guess, not complicated, but it's a little involved, right? So I hope that made sense, and I'll go over it, I guess, again when I show you the code. So you kind of have to understand how this works, so you can also understand why my code is written the way that it is, okay? If this didn't make sense, what I just said, let me know, and I'll try to explain it in the comments or something. Okay, so we're going to jump into the code. Alright, first thing I'm doing is I made some functions here just to initiate the stuff. Init I2C is just a function I made. Let's make it bigger. And all I'm doing here is obviously I'm enabling the clock for and I'm using I2C2, by the way, just because this thing, it's wired to I2C2, so I can't modify this circuit. It's not a breadboard or anything, so it's wired to IC2 on that chip. Excuse me. So I'm enabling the I2C2. Why do I have it not enabled? Oh, I don't know, because I think this was when I was going crazy trying to figure out what I was doing wrong with all the I2C stuff. So I was resetting everything to 0 and then enabling everything just to make sure that I'm starting with known values. So yeah, so you don't necessarily have to do that. I enabled a GPIO B because that's where I2C2 is located, and here I actually enabled the I2C2. I had enabled the interrupts, but again, we're gonna use DMA. We're gonna use DMA for the RX. I'll show you how to use the regular flags for the TX. And then remember, in control register 2, we're going to write those frequency values of the APB1 bus where the I2C. So that's control register. So right here, I'm writing the number 36 into that control register 2. Okay, now we're going to get into this whole the timing thing. And this is where the calculator is going to come into play. Alright, so, and I've try to explain it here, so you can pause the video and try to read this if it helps. So we're gonna take the period of the value that you just put up here, right? So this is 36 megahertz. So we're going to take the period of that, which is 1 over 36 megahertz, and then we're going to get a value. Then, so let's first do that. So we have the APB1 bus. I wish I was righty, so then you can see what I'm writing here. But APB1 is at 36 megahertz, okay, and we're gonna get the period, which is equal to 1 over 36 megahertz, and I'm gonna whip out the old calc. So that's 1 over 36 e to the 6. That gives me 27 point you can't even see that, 27.7 nanoseconds. 27.7 millimicro nano, nanoseconds. So that gives me 27.7 nanoseconds. Okay, so let's see what's next. So I have that value. Then it says now we're gonna pick a frequency that we want the I2C to run at. So in my case, I'm gonna use 100 kilohertz. So then we're gonna get that frequency. We're gonna get the period of that. So we're gonna get the period of 100 kilohertz, and then we're gonna divide by 2 because we're gonna use that. I want the high time and the low time to be equal, so it'll be basically like a 50% duty cycle. So we just divide by 2, and we're gonna get basically 5 microseconds. So 100 kilohertz, the period is 10 microseconds. 100 kilohertz, and then we divide by 2. Then our period is not our period. The duty cycle. What the hell am I reading here? Divide by 2, you get the high time. All right, so we get this number, 5 microseconds. All right, so then what we're gonna put in this register is going to be these 5 microseconds divided by what we got from the period of this thing, which is 27. So in that CCR register, you're going to get that 5 microseconds. Well, I'm gonna write it like this. You're gonna put your I2C period. Let's call it period divided by 2 over this. So 27.7 nanoseconds. So you're going to take the period of your I2C, which we said was where's the eraser? So we said we wanted an I2C frequency of 100 kilohertz, right? 100 kilohertz. We got the period of 100 kilohertz is 10 microseconds. We divide that by 2, and that gives us 5 microseconds. So the I2C period, which is right here, T of I2C. So this I2C period divided by 2, which is 5 microseconds. So this is all 5 microseconds divided by this number that we figured out here. So it's going to be 5 microseconds divided by 27.7 nanoseconds. So whip out the old calc. We're going to have 5e to the negative millimicro 6 divided by, I'm going to copy that and paste it there, enter. That gives us 180. So this whole thing equals 180. So that's the value we're going to put in this register, 180. Oops. I hope this makes sense, and I'm going to explain it one more time just for clarity's sake. You first find the speed that your APB1 bus is running at, and if you're running your microcontroller at 72 megahertz, then the APB1 is half of that, so 36 megahertz. Okay, then you're going to find the period of that. The period of any frequency is 1 over the frequency, so it is 27.7 nanoseconds. Alright, so we got this number saved in our head. Then, and we're just doing all of that because we want to figure out what to put in this CCR register. So then you're gonna pick a frequency that you want for your I2C. I chose just generically 100 kilohertz. Where am I? 100 kilohertz. Okay. So then we're going to find that the period of that 100 kilohertz. So the period of 100 kilohertz, it's 10 microseconds. So then we're going to take 10 microseconds. We're going to divide it by 2. You get 5 microseconds. So this whole top part is a I2C period divided by 2, which is what we just did right here. It's 5 microseconds. So this whole top part is 5 microseconds. Then we're going to divide that by this number that we got up here that was saved in our head. And once you do that, it gives you the beautiful number of 180. That's the number we're going to write in this CCR register. Okay, you little YouTubers. So, there you go, 180. Easy peasy. Then we have to write the T rise time. And again, I'm getting this formula and all this stuff from the data sheet. So you can go ahead and read that if you like. Then that's going to be this. Well, let me erase this. What do I erase it? Nah, that little eraser is not going to cut it. I'm going to use this microfiber. Erase this board. Oh man, that looks terrible. Anyways, YouTube doesn't care. You guys just want the knowledge. Alright, so now to do that, let me transition here. So we're going to take 1,000 nanoseconds. We're going to divide by CR2 period equals 1 over 36 megahertz. So by 1 over 36 megahertz. What's nano? Milli, micro, nano is so this nanosecond is really one microsecond basically. 1 e to the negative 6 divided by parentheses 1 over 36 e to the 6. Okay, so you take this 1,000 nanoseconds, which is the same as 1 microsecond. You divide it by this, right? Which is the what you call it? That 36 megahertz we just talked about earlier of your APB1 bus, and you get I forgot what that was. I think that was 27 nanoseconds or something. You'll get the number 36. Then you're gonna add 1 to that number plus 1, and you will get the number 37. And I repeat, getting this from the data sheet. Don't ask me why it's 1,000 and why we're gonna add 1, but there you go. You get the number 37. So 1,000 nanoseconds or 1 microseconds divided by the period of that APB1 bus, and you get the number 37. And then that will go in this T rise register or section of your register. That goes right here. Okie dokie. So once you have that, then we're gonna go into the control register 1. I enabled the acknowledge. Stretch mode is enabled by default, so we don't have to do that. 7-bit addressing mode is enabled by default. Did I even show you that? Because I just not sure if I remember showing you that. Where the hell is it? I'm sure I did. Because these things have different addressing modes. Where the hell is it? Where is the addressing mode? Oh, right here. Bit 3. This you're just telling the the I2C that your slave either has a 7-bit. Nope, this isn't status register. That's not it either. Holy crap. I'm not sure, guys. Oh yeah, this doesn't even well, this is only a 7-bit register, so you can't really put a 10-bit address in there. Okay. Maybe I'm thinking about the other microcontroller where there's a specific bit where you set the this does support. Anyways, I don't know. I haven't used 10-bit addressing, so but in the other microcontroller there's a specific bit to set 7-bit or 10-bit addressing. Okay, so don't worry about that. Oh yeah, another thing you have to remember, I2C needs pull-up resistors on the data and on the clock lines. So in this chip, I don't use it because the chip already has it has pull-up resistors. You can't really see it, but they're right there. So I don't need to enable that. But if you do need to enable those pull-up resistors, you would do that in your GPIO registers, and that's just a matter of after you configure it to alternate function mode right here, then all you have to do is just basically act like you're just setting them high, right? So and that'll pull them up via the internal pull-ups. So you just set those pins high, and then that'll enable the internal pull-ups. Here are the events for interrupts, which I didn't use like I was telling you. And here I finally enable the peripheral. Alright, so that's all you really need to actually configure. But it's there's more stuff that we have to do once we get going, which is the actual RX and TX. So just enabling your clocks, enabling the peripheral, setting the frequency of the APB1 bus, doing these two calculations for this. I enabled the acknowledges. I configured the GPIOs to be in alternate function mode. I'll put open drain, and then that's it. You know what? Let me show you on the data sheet. Well, I'm pretty sure you know how to configure the alternate functions. Gosh, these data sheets are so massive, it's really annoying. Alright, so here it tells you how you should I2C. So here, I'm not just magically guessing that I need to put it in alternate function mode. It's in the data sheet. So here it tells you that in I2C, this is page 168. For I2C, the clock and the data pins have to be alternate function open drain mode. Because there's also, I think, alternate function push pull, I believe. And there's different modes. So it needs to be an alternate function open drain. And you do that in your GPIOs. Control register high and low. Yeah, so there's alternate function push pull, and then there's alternate function open drain. So you're going to use the open drain configuration. Alright, so I'm not just pulling that out of the air, guys. Okay, yeah, and then I enable the peripheral. So now let's get into the actual writing. Now I named this write single for some reason, but it doesn't mean anything. You can just throw in a for loop in there and write more than one byte. Alright, so the first thing that needs to be done is I made a temporary variable here. Just you'll see why in just a second. So the first thing you do when you're gonna initiate communication is you're gonna send your start condition. Once you do that, you're gonna check the status register 1 for that SB flag. That means that your start condition was sent. So once you exit this, it's because that flag was set. So you exit that, And then the next step is to transmit the address, the device address. So that's what you see here. This is defined to the address of my my EEPROM. So then you put that device address into the data register. Then you wait for that ADDR flag in the status 1 register. What this flag tells you is that there was a match for that address. So once there's a match and that flag becomes set, then this it'll exit this while loop. And to clear that flag, you have to clear this flag. To clear that flag, it requires that you read status register 1 and then status register 2. So if we go back to our status register 1, here is the ADDR flag, and it's bit 1. So let's scroll here. As you can see, it tells you this flag is received address matched. This bit is cleared by software by reading status register 1 followed by reading status register 2. So you have to do this, read this, and then read that to clear this flag. That's how the flag is cleared. So by default, while I'm checking for the flag, I'm already reading that register, right? It's being read in this while loop. So once it's set, so that part is taken care of. Once it's set, to clear it, all I have to do is read the other register. And that's why I put that temporary variable, because I'm reading it, so just storing it in there, not doing anything with it. And that's why I get all these warnings when I compile, because it says, hey, you're not doing anything with this variable. So screw you. Anyways, so once you have an address match, then I send it the memory address, the internal address, right here, because this is a write operation that I'm doing. So I sent it the address of the EEPROM. Now I'm sending it the address of where I want to write my data to, and that's mem address. And remember, this is a function, so here's device address and here's mem address. And then I wait for that transfer to be complete, or in other words, I wait for my TXE buffer or flag to be set, which tells me that it's I can go ahead and put more data in the register, in the data register. So once that exits, I put more data in the data register, and what I put there is data, and data is right here. So I'm going to call this function, and I'm going to pass it the device address. I'm going to pass it the memory I want to write to, and then I'm going to pass it the actual data that I want to write. Mem address. So once that's done, I don't know. This was some testing, I guess I was doing. Don't need that. So once this, every time you send data, you're gonna use this while loop here to test that, to wait for that data to be sent into your shift register, so then you can write more data in here. But then I'm just doing 1 byte, so then after that sent, I send a stop condition. Now, if you're gonna send it more than 1 byte, obviously you just put a for loop here, and maybe you can pass another variable here called length, and then you put that for loop here, and you just keep doing this until length equals 0. Obviously you're going to decrement, and then you send your stop condition, right? So that's for you guys to figure out, which I'm sure you can. And then you send your stop condition, and that's it. So that's the write. Okay. And I'll go ahead and show you what that looks like in pulse view. So let me whip out pulse view real quick. So let me show you what it looks like in the code first. So as you can see here, I call that init function. I have a temporary buffer. A lot of this code is just left over from tests that I was doing. I probably don't need that, and I'll compile just fine. Oops, x is undefined. Oh yeah, I do need that integer x. That x is just something I'm using for something. I'll tell you in just a second. This is just waiting for me to press a button on my on the board here, because I don't want it to loop a million times. That X variable, I'm just using it because I'm gonna press that button, and then I'm gonna increment X, and then X is gonna be greater than 0, and then it's gonna do nothing. So long as X is greater than 0, it's gonna do nothing. So that means it's only gonna run this code one time, because I don't want to fill up all of pulse view and you can't tell what is what. So I just want this to run one time. So here's what I did, and right now I'm just showing you the write operation, the function. So yeah, so here's the write operation. I said that the EEPROM address that I have, I want it to write to address 4, and I want it to write the number 60 or the hexadecimal 60 in there. And then I delayed 2 milliseconds because in the data sheet for the EEPROM it says it takes it about 2 milliseconds to actually write data. So then I delayed 2 milliseconds, and then I wrote another byte. I wrote it at address 5, and in there I wrote the number hexadecimal 61, and so on and so on. Okay, so now let's go over the read operation. Again, I have another temp variable that really just helps me clear some flags, and here I have the I2C buff 0 or whatever. This I think I have this buffer globally defined up here. This I'm not sure why I have this set to 0 here. I'm pretty sure I don't need it. Anyways, so in this, for the read operation is where it's really troubling. So I used the DMA, right? So I went to that control register 2, and if you don't know what the DMA is or haven't used it, go to the previous videos I uploaded yesterday or the day before, where I explain how to use the DMA. So I have here control register 2, I enabled DMA. Notice I didn't enable it in the TXing, because for that one I was showing you, where is it, here, just how to use the flags and check the flags and all that stuff. But for this one I am enabling it for the read. So I enable the DMA in control register 2 of the I2C. I also enable the acknowledges, and then I go ahead and I configure the DMA. I give it the address of the buffer where I want it to store all the data it receives in the I2C. Then I give it the address of the data register for the I2C, so it knows where it's reading from, right? Then I should have passed it len here. So then I tell it how many bytes I'm receiving, how many transfers it's going to do from the data register to my buffer. And then I go ahead and I enable the transfer complete interrupt for the DMA, the memory increment, and then eventually I enable the actual DMA. Now the cool thing is that once you there's nothing else really you have to enable for the DMA, because it'll start right off the bat once you send your start condition. So I send the start condition, and obviously I have to wait. The DMA is not gonna, it doesn't know what address I'm writing to, right? So I have to do these two steps: send the start condition myself and send the address myself, and then the DMA will complete the requests, because the DMA doesn't know what address I'm writing to, right? All right, so I send the start condition just like we did for the TX part. And I send the start condition, and then I wait for that SB flag that tells me that the start condition was sent. Then I send the address, and as you can see I added 1 because the address is 1010. With those 3 pins grounded, it is 000, right? And then the 0. That's what device EEPROM address, when I call the function EEPROM address, where is it? Right here. So it's 1010 and then 4 zeros. So that's what it's defined to. But that address is for write operations. When I want to do a read operation, that becomes a 1. So that's why I did +1 here, to send it a basically when you send an address with a 1 at the end, it signifies a read operation. So then I send it the address with the 1, which means a read operation. Then I wait for the address match to happen. Once the address match happens, I read status register 2 to clear that flag. And then I just sit here and I wait for the transfer complete from the DMA. I wait for that flag to be done. Once that flag is set, that means the DMA is done doing its job. And then I disable, or I send the stop condition on the I2C. If you were not doing this with DMA, this right here would be a whole lot of code. If you're receiving, right here we're receiving 5 bytes, we would have to receive the first 3 bytes, then go into receive 2 byte mode, then go into receive 1 byte mode, and it's a mess. And right here we're just waiting for the DMA to take care of all that mess. So upload, I'm gonna switch over to post view now, and I'm gonna go ahead and run the whole thing. Really great time for post view to freeze. I have to restart it. Close the program. I know you guys can't see anything, but I had to restart it. So let's see if it opens up properly. And it detected my thing. It did. Let's put 3 megahertz, whatever. Oh no, I think I usually set it to 2. I don't know, whatever. We'll do 20 million samples. Nope, that's not working properly. 4 megahertz. It's not really that. It's my okay, there it is. So here is all the now the reason I have to start and restart, and because you heard me pressing all those buttons, is because this EEPROM is so fidgety. It is so fidgety. I'm always having to press reset to reset that EEPROM. Okay, so let me go into the zoomed in version of post view here, so you guys can see that. Let me actually change this, because you don't need to see that from that post view screen. Sure, yes. Alright, still has the outline. Okay, so these are these smaller ones that you see right here. These are all the write operations that I did, and then this longer one is the read operation. And you're gonna see some interesting stuff here. Oh shoot, I gotta set up the take that off, and we're left with just those 2. And then we're gonna enable I2C decoding. Actually, this has an actual decoding for this specific EEPROM, and we can just go ahead and do that. Okay. EEPROM, my clock is on 4, data is on 2. There you go. So it actually tells me what I've done to the EEPROM, this extra stuff here. Alright, so here is this the first one? Yeah, okay, so here's the first write operation that I did. As you can see, I sent the start condition, that's what that R is. I sent the address with a 0, which indicates a write operation, and then I got an acknowledge. And as you can see, since this software knows that I'm using this chip, it's telling me that those pins A2, A0, and A1 right here are zeros. So anyways, I got the acknowledge. So after I sent the address, I wrote the address 4, and in the address 4 I sent it that. So as you can see here, that's the very first thing I did. I wrote the EEPROM address. I wanted to write the numbers hex 60 into the address 4, and then I did 5, 6, 7, 8, 60, 61, 62, 63, 64, and then I did address 3, write the number 65. So that's what all this is doing. So I got 4 and 60 there. I have address 5, I wrote the number 61, or hex 61 rather. Address 6, I wrote hex 62, and so forth. Address 7, 63, address 8, 64, and then I went back down to address 3 and I wrote 65. Now why did I do that? Because I want to do now a read operation, right? So now my read operation, I wanted to read from address 4 all the way down to 1, 2, 3, 4, 5 to here. So I wanted to read all these bytes that I just wrote, right? So I wrote all these bytes, and I want, so no, what did I, oh, address 4, yeah. So I want to read these bytes, so the pointer's somewhere over here. So to start reading from here, I had to send it send it to 3, so then it could increment. So then when I do the read operation, it'll start from here. So that's why the last write that I did was to 3, and I just wrote a random number of 65 or something there. And actually, let me, because I don't want to confuse you guys. Well, you'll see. I'll show you in just a second. So here's a read and the EEPROM address and the length of 5. So then here it is. So here's the read operation, right? And you can see now that the read bit is 1. So that means read. I got the acknowledge. Then it started reading from address 4. And at address 4, I wrote 60. So that's correct. And then I wrote 61, 62. So that's all correct. However, if you notice, my length was 5. That's how many reads I wanted. But there's 1, 2, 3, 4, 5, 6 here. So I have an extra byte. Now that kind of sucks, doesn't it? Because that means the DMA didn't work properly or something. Well, actually, no. The DMA worked exactly how you want it to. This is just a bug of the I2C, or I guess maybe even the DMA couldn't take care of the race condition or something. The point is, I do have this extra byte. But let me show you now the code. So remember, in this read thing, I stored all of the information that I was reading. I had the DMA stored into this I2C buff. So let's open up the debugger. I'm not even showing you guys the freaking thing. Okay, so I've opened up the debugger, right? Because like I was just telling you, in the read function right here, I had the DMA store everything into I2C buff. So I want to see the values that are in I2C buff. So I'm going to place, so I'm going to run this code. I'm going to have it just pause once it enters the read function. I'm going to execute all of that, and I'm going to just have it pause here at the end of the read function. And I want to check the values of I2C buff, basically. So let's run it. I'm going to press that button, and then I'm going to run again. And now I'm at the end of that read. So now I'm going to check my I2C buff. And there it is. I know I can't zoom into this, but I hope you guys can see if you can make it out. The 0 index of I2C buff has the value 60. The 1 index has 61. The 2 index has 62. The 3 index has 63, and the 4th index has 64. So it indeed transferred the 5 bytes that I wanted, and they are clearly written in the EEPROM because these numbers match. But as you can see, that 5th extra byte that we have is not in my buffer. Why? Because I told my DMA to only transfer 5 bytes, 0 to 4. And that extra byte that we got, it didn't transfer it. And that's great. That means the DMA did exactly what I wanted to do. So that extra data that did come through on the EEPROM or the I2C, it completely ignored it. So yeah, the data came through on the pins, but we didn't do anything because I only told the DMA to transfer the 5 bytes that I wanted it to transfer. So as you can see, even with DMA, the I2C on this peripheral is still a little buggy. And that is that as far as the that code is concerned. Again, if I'm not even sitting here right now, I'm not completely happy with the way I've presented this tutorial. So if you guys didn't understand it or something wasn't explained properly, I can surely explain it again. In fact, I'm even getting the urge to take the whole TX the TX part and convert that to DMA just to be more concise. I just wanted to do one DMA and one TX to show you regular one DMA and one regular to show you guys the differences. And definitely I would encourage you to use DMA for both, just because it'll be a much easier procedure and less buggy. But anyways, guys, let me know, or if you want, you can try to implement the DMA for the TX part all on your own, based off of what I did here and based off the the last 2 DMA tutorials I did. So yeah, that would be a good exercise for you guys too. So I hope this helps. The next thing I'm going to do will probably be SPI. As far as STM32 stuff is concerned, will probably be SPI, unless you guys really want me to go ahead and make those videos on communicating with the sensors. All those sensors that I used for I2 for the STM32 are actually I2C. In the meantime, though, before I do that SPI video, I might release more videos on my motor controller thing that I'm working on. Anyways, guys, so let me know how this video was. If it's a good, bad one, terrible, I don't know. It's Saturday, man. I'm gonna go have a beer, buy some chicken wings somewhere, go out with my wife. She'll be home soon. Later, guys.